All right, on to lesson 3 of how light and matter are similar. So, again, looking at that photon and that that energy absorption by certain elements, for example, and then being able to knock out photons. So, also the other thing that we mentioned about is that electrons moving between energy levels in an atom. And so each atom, it turns out, has its own series of energy levels. And here's 3 examples here. So we've got hydrogen on the left, we've got mercury in the middle, and then some sodium on the right. Now you notice there's a couple of different ways that it can be written and set out. So let's look at the one here on the left here. So the hydrogen atom, N equals 1, is what we also known as the ground state over here on the. Alright, so that's the normal. So you got electrons wanting to sit, or the electron in the hydrogen atom wanting to sit here. Alright, and that's where it would like to sit. Now if you put in a photon of the correct light, you can get that electron to move up depending on what that energy of that photon is. It can move up levels, and now you'll see here it's written in negatives, so it might go here up to, say, this first level here, N equals 2, the first excited state, it's also known as negative 13.6 to negative 13.4. So it's the difference between that. And so ionization, when we rip the electron out altogether, is up here, and that's energy level of 0. Let me just get all these scribbles. Alright, so what this means down the bottom, at negative 13.6 means you need to put in 13.6 electron volts of energy to rip that electron out. Now you notice the sodium one, it's labelled differently, so that's 0 ground state. Is 0, and up here ionisation 5.13, I should say. So what you need to do to an electron in the ground state of sodium, that would be an outer shell one, to rip it off you have to put in 5.13 electron volts. Alright, so it's the difference between those is what we're after. Alright, so if an electron moves, so if the energy of the photon that's required will be the energy of the higher level minus the energy of the lower level. Now it doesn't matter which way of describing that whether we're using the hydrogen one here where it's negative 13 down there, or the sodium one where it's 0 down there in its ground state. Doesn't make any difference as to which one you use. You can still use this relationship that the energy of the photon is there. And now, of course, the photon energy we've already done is HF. So the energy of the photon required is given by the high level minus the lower level, and then you can figure out what frequency and hence what colour that needs to be. So if we want to look at a little bit more detail at hydrogen, and this diagram's in your notes, that part's missing in your notes, just on that first page there, underneath where it says an electron moves from a higher to a lower one, the energy will given out in the form of a photon. The energy of the photon is given by that. Alright, here's a bit more detailed diagram of hydrogen. And so we've got N equals 1, the ground state, N equals 2, first excited state, and so on. So if I put in some energy, so here's my electron sitting there in hydrogen where it minding its own business, and I put in enough energy, and that would be 13.1 electron volts, I can get it to come up here. Now, that's the fourth excited state, N equals 5. There's a few different pathways for it to get back down. So you could see a few different colours. So when it's up here, it could just drop to this next one. Or it could drop to the second one. Or it could drop all the way down here, and I've just gone over that, which was blue. So let me change to blue down here. And so over here on the right, where you got your shell diagrams, that's from this one here down to there. That's this one. All right, so initially it was sitting in here and then went up there. All right. Or it could, of course, drop all the way down to the bottom, which is this one. All right. So if it drops a series of other steps and it ends up, say, in the third excited state, there's 1, 2, and the green one, 3 different ways that could drop to there. And so there's the green one, here we go there, that's this one in here, from that shell to that shell. Alright, if it ends up in the second excited state, well, it could go, there's 2 ways. There's that red one, which is there, or it could, of course, go all the way to the bottom. Now, of course, if it ends up in any way at the second excited state and then it drops down. So, depending on what pathway it takes, you can get different energies for the electron. Alright, okay, so here's just another little diagram. So if you've got an electron up here in an excited state and it drops down here to this one, you get a photon out. If on the other hand you've got an electron down here and you've got the photon of the right energy coming in, that electron can jump up. Alright. And so depending on which is which happens, sometimes here it's absorbed and over here you get the photon out. Alright, a couple of examples. And there's 21.15. What is the energy of photon emitted when an electron or sodium falls from the 2.1 eV level? So there's the 2.1 eV level there to the ground state. Alright, so the energy is the difference between those with the higher minus the lower. And so the higher is 2.1 and the lower is 0, so simply 2.1 electron volts. Alright, so it says the energy of the photon that's emitted. Second part of the question. Alright, so the second part of the question, I'll do this one in blue. It says the 3.75 eV level, which is there, down to the 2.1, which is here. So, again, if we're looking at the energy of our photon, it would be the energy of the higher minus the energy of the lower, which is 3.75 minus 2.10, and so that is 1.65 electron volts is the energy of that photon. Alright, next example. Example 2. Alright, what is the minimum energy required to ionize a hydrogen atom? Alright, I'm going to shoot back here. To this page here. And let me just get rid of a couple of those squiggles there. So here's the hydrogen one. And it says to ionize. So if we're going to ionize, we've got to take out from there out there. Now, it says the minimum energy because you could give it enough energy so that not only would it get out, but it will keep going. So the minimum energy is to get it up to here. So we're looking at that there. So the higher is 0, the lower is 13.6. So let's head back. Alright, so energy of the photon is the energy of the higher minus the energy of the lower. So 0 minus negative 13.6. And so that is 13.6 electron volts you've got to put in. Second part of the question asks you what frequency that this is involved. So the energy of the photon is also HF. And the energy of the photon is 13.6. It's a bit messy. Let's get rid of that and redo that. 13.6. H, Planck's constant, because that's in EV, we need to use the EV version. So 4.1 by 10 to the minus 15 times the frequency. And then when you divide both sides by 4.1 by 10 to the minus 15, you get 3.32 by 10 to the 15 hertz. All right. So all of that idea of electrons moving between energy levels and light being given off, photons being given off, leads us to the idea of an emission spectra. All right, so here's the idea behind it. An emission spectra. We have what's called a discharge tube. Essentially, it's just a tube filled with some sort of gas. We put a high voltage on it. Some of the electrons get excited. They move up and then they drop off. And when they drop off, they give off light. And we put through a thing called a spectroscope, which essentially just diffracts the light and spreads out the colours. And then what we notice is that there's what we call a line spectrum. So we get these, they're shown in white here, these bright lines of colour. Now these bright lines of colour are not any random, but they're colours relating to the movement of the electrons between the energy levels. So in your notes there under that diagram, above that diagram in your notes there, in the third sentence in that above that, it says the frequency of the light emitted depends on the energy levels of the electrons. Thus each element has its own emission spectra. And then under this diagram, frequency of light emitted corresponds to the difference in energy levels of the atom. All right. So then the next bit we've got this diagram, and above this diagram it says applying voltage to the gas excites the electrons to a higher energy level. When they drop back to the lower energy level, release a photon of light. Metal vapor lamps produce this type of spectrum. So here's some spectra, some line spectra. So we'll not worry the bottom one. Leave the bottom one for the moment, but you can see hydrogen, helium, neon, sodium, mercury. You can see that their spectra, the lines are all in slightly different places. Okay, so what that means is that the energy levels that the electrons can be in those atoms is different. Now this bottom one here is the mercury one, but what they've done is they've graph the intensity of each of those lines. So the yellow one in the middle for mercury is much brighter, and then these others particularly these red and orange ones down here, are not very bright at all. Alright, so difference in energy levels, and you get that. Alright, and we can observe that, so we can observe that there is some sort of photon packet of energy that's given out. Now also, of course, if photons can be given out, why can't they be absorbed? And the short answer to that is, well, they can. And so that's why you get an absorption spectra. So if you have a cloud of gas or something like that, and then you have a light source in behind it, and then that light source shines through the cloud of gas, you could get electrons being excited in the atoms, I should say, in the cloud of gas. And again, you would have put it through a spectroscope and you could observe these lines. Although this time, because the photons here that are going in here are being used to excite the electrons, those frequencies relating to that get absorbed. Alright, and so this is how these two things is how astronomers figure out what stars are composed of, because we can look at line spectra here on Earth with stuff we know, and then we can have a look at stars and see whether they have the same ones or not. Alright, so in your text there's a bit on pages 350 and 351 on the Bohr model worth reading. Now, of course, on the website there's also there's a video on the Bohr model there. There's also some spectral line, emission line, and absorption line videos on there. Some explanations and also some experimental some experimental stuff in the videos actually showing you what happens. So have a look at those. Alright, absorption spectra, this is what they look like. Alright, so there we are. So up the top here, so if we shine light through hydrogen gas, we can get electrons to jump between shells. And so you can see there's now dark lines in these places. So these dark lines, those frequencies, those energies have been absorbed to get the electron to move up in the transition. And the emission spectra down below, and so you'll notice you can see that these line up. And so just a matter of interest, not something you need to learn, but that particular line there is between n equals 2 and n equals 3, so the first and the second excited states. Alright, Bohr and energy levels. So Bohr came up with this model, mathematical model, and there it is down the bottom here for the energy levels depending on n, what n is. Then the energy of that level is negative 13.6 over n squared electron volts. Not something I really expect you to remember, but just to illustrate that there is a mathematical model for hydrogen. Higher ones, bigger atoms, far more complicated. Hydrogen, because it's only got the one electron, much easier, and so Bohr's model is up there. Now, also, excuse me, there's these series of photons or lines, if you like, with some names. Again, this is a matter of interest, not necessarily something you should know. A thing called the Lyman Series, so that's any electron that goes from an excited state to the ground. The Balmer is from any excited state to the first excited state, any higher, and the Passion from any down to the second excited state, n equals 3 from any higher. Alright, so even though it doesn't explain this model for more complicated atoms, it still gives an idea that, you know, there are some discrete energy levels for the electrons in the atom. Alright, so underneath that there's a sentence that says the model could not explain the energy levels more complex, however it was significant in suggesting discrete allowable energy levels. I already mentioned that. Then under this there's a, that sentence under that there's a missing word. So in the development of his theory, Bohr made links to the quantum nature and provided a conceptual framework for future developments, particularly those of Heisenberg and Schrödinger. So we'll get to Heisenberg and Schrödinger a bit later. Alright, there is an example. So calculate the wavelength in nanometers of the photon produced when the electron drops from the n equals 4 level of hydrogen atom to the n equals 2. So we need to know the energy of level 4 and the energy of level 2. So let's go back to that. Alright, so level 4, so there's 4 up here, that's this one, negative 0.85 eV. Level 2, there's n equal to negative 3.4 electron volts. So the change in the energy, which will be the energy of the photon, is negative 0.85 minus negative 3.4, which is 2.55 electron volts. Now in this one here, it asks for the wavelength, not for the frequency. So remember, E equals HF, but using V or C equals lambda F, the frequency is speed of light over lambda. So what we're looking at here is that the energy equals hc on lambda, and if we rearrange that, multiply both sides by lambda, divide by E, you get that the wavelength is hc on E, and so the wavelength would be H, and because it's electron volts here, the electron volt version, 4.1 by 10 to the minus 15. Let's go back, I've forgotten what it is. Whoa, hope you're not spinning out. There it is, 1 minus 15. Let's go back to the end here. Don't get sick while we're moving. 10 to the minus 15 times 3 by 10 to the 8 over 2.55, which comes out to be 4.87 by 10 to the minus 7 metres. It's in a funny place, that metres. Okay, and if we move that decimal point a couple of places, 487 nanometers for the wavelength of the light that's given off when it travels, an electron travels between those two energy levels. Alright, now electrons, waves, energy levels. Alright, so we're connecting. A few of these things are getting thrown around, and there seems to be connections between. So our old friend de Broglie, it's probably not how you pronounce it, but anyway, Alright, and his waves and his matter waves and that, he pictured the hydrogen atom, or the electrons. He pictured them travelling in waves. Can't spell there. Alright, so travelling in waves. So what he said was that the allowed orbits corresponded with a wave. And so if you have a whole number of wavelengths, so wave, that's the first missing letter, so a whole number of wavelengths, and that's in the second bit, is needed to form a standing wave. And then if it does that, then it's all happy and away it all goes. And so if you want to try and picture that, you'd picture it something like this. So the blue lines there are the circumference of the energy level, and so whatever that particular energy level, and you can see in the red it's kind of like a wave. So well, there's two of them, the standing wave. So the solid one, we get our trough, then we get a crest, then we get a trough, then we get a crest, and it joins up and keeps going around. Standing wave because it oscillates backwards and forwards this way. All right, and then so that's two wavelengths that fit in there, trough, crest. Or you could get one where you have four, and that's in this middle one, or you could get one again which would have 9 wavelengths fitting in it, and then it'd all be happy. But what he said was, though, if the number of wavelengths is not correct, what you get eventually is you get something like this happening. So those waves don't join up, and so you end up getting some interference, and you end up getting destructive interference, and so that therefore can't exist. So underneath that is a couple of words missing. Electron wave whose wavelength is slightly longer or shorter would not join onto itself smoothly or quickly collapse due to destructive interference. Only orbits corresponding to standing waves will survive. Alright, so i.e. stable orbits of a hydrogen atom are those where the circumference is exactly equal to a whole number of wavelengths. Alright, so the last bit got here, and that's in the study design. It says to compare light sources. So there's a few different things. So incandescent light, which is kind of like your normal light bulb. All right, so you heat up a metal. This is what you get out of it: continuous spectrum. LEDs, in the middle there, we get specific colours depending on what they're made of. Lasers, again, we get specific colours depending on what they're made of. And then you've got synchrotron light, which we can produce a lot of wavelengths, but they're extremely bright. Alright, so that table, I guess, is something you might try and squeeze onto your sheet of notes somewhere. It's in the study design about the comparison, but it's because it's the first time in there, it's a bit unclear as to what they were thinking when they did it. But nonetheless, it's there, so we need to cover it. Alright, let's set number 3. So there's a few videos there that are quite good, 9 of them altogether. They're quite good, give you some good explanations and some good examples, graphics and animations and stuff like that. And of course, if you've got any questions, make sure you ask.